Okay, so we're starting the next stage of our processing. So this is going to go through a whole series of steps. So we'll create a new directory for that. We're using those four pulsar tiles that we've already created in our stage 2 processing. So we're just going to copy those into this new directory rather than reprocessing those. So that's what we're just doing here. We're now copying some of our scripts. So I've got two versions of this Mosaic script. The first version specifically names the files, and we'll just have a look at that now. So you can see the file names explicitly listed in the input list. And then the second version, which we're just looking at, uses the glob module, so that rather than searches the file system and finds the input files at runtime rather than having them hard-coded. You can run either of these scripts, they'll both produce the same results. Okay, so we're just coming to the end of our mosaicing, and now if we list those files, you can see that mosaic file has been created. So the next part of the processing is to resample one of our data sets to be the same as the other. So we're using Landsat and we're going to use the pulsar data. So the Landsat has got a nominal resolution of 30 meters and the pulsar 25. The Landsat is in UTM projection while the pulsar is in lat long. So we want to resample them so that they match. So in this case, we're resampling the pulsar data and we're going to make it match the Landsat image. And we're using this RSGISLib function which resamples one image to using a reference image. So using the Landsat image as reference and resampling that pulsar data. So just finishing that processing, and if we list our files, we can see that we now have our image, which is in UTM projection, same pixel spacing as the Landsat data. So the next thing we want to do is create a valid mask imagery. So this is a binary mask that's going to say which pixels in both data sets have a valid pixel. So if we run that, it should be pretty quick to run. Okay, so if we list the directory, we should be able to see that that file is there. So we've got valid Sundraban's valid mask.kia file. So the next processing we're going to do is we're going to convert that valid mask to a vector data set. So this is just quite useful for being able to put have a layer that we can easily put in our GIS, overlay other layers, and things like that. So while it's not strictly necessary for the rest of the processing, it's just quite a useful thing to have. And as we've generated it, we're going to use it to subset our data sets to the same area of interest as well. So if we just look in there, you can see it's using a function called Polygonise Raster to vector. You see we're outputting to an Esri shapefile. You could be outputting to any vector format that GDAL supports. And you need to provide the file name and then the layer name. If it's a shapefile, the layer name is just the same name as the file. So that's run through. You can see we now have that shapefile. It can quite often be useful to rasterize data, so that means to take a vector and to rasterize it onto a grid, and this function, the script here is just demonstrating that. Okay, so that shapefile that we created is basically defining a region of interest where we have valid data. So as the extents of our two data sets are slightly different, just to keep things efficient and make our processing later on a bit quicker, we're going to subset both the Landsat and the Pulsar data to that same extent, which you can see here in the script using this subset command, passing in that vector data set as the region of interest extent that they're both going to be subsetted to. So that's just going to run through now. So on to the next processing stage. So we've now got these subsetted images spatially subset, and we just want to mask them so that we have valid pixel values in both images. So we're using that valid mask that we created, and simply we're masking out, making no data, any pixels which aren't valid in both of those data sets. So we can just run that through. Okay, so we've masked it, so we have valid, both data sets, we have valid data. We're now going to subset the bands that we have in our image. So this may seem a little bit of an odd thing to do, seeing that we stacked an extra band into our pulsar data, and now we only want the first two bands, the two polarizations HH and HV. And this is because we're then going to do a filtering, and we should only be doing that filtering on those two data sets. So this is just extracting those two bands, effectively dropping that third ratio band, which, while useful for visualization, in this case we don't want it for some of our later processing. So that's now run through. And we're now going to copy in another script which is going to provide a smoothing filter, Lee filter, to our data. So this is going to reduce the speckle in our SAR image, the Lee speckle filter. So we're just going to run that. This is running on the HH and the HV band, not on that ratio band, because we just dropped that band in the previous step. Okay, so that filtering is finished, and we now want to convert our radar data so the pixel values are decibels rather than power. So we're just copying that script in. We'll have a look at it. So this is basically doing an image maths, which is similar to band maths, but you basically apply the same function to each of your different images. So B1 is the band value, and that's done for each band, so the same equation to each of them. So in this case, it's 2 bands, applying the same to each. So the next and final step of this pre-processing work is to calculate some indices from our Landsat data. So we're interested in the water band index, and we're interested in the NDVI. So just copying that script into our directory, we'll have a look at that. So this is using that bandmath function. Again, you're probably familiar with these indices. So we'll now run that through, and then we'll have NDVI and water band index images that we can then use in our classification step. And one of the real advantages of doing this process where it's all scripted is that it means if we want to change something in our processing chain or run it on some different data sets, then obviously we can combine this all into one script. And if you look at script number 13, that has combined all of these steps into one script, so you can process it all in one go.